So what we're going to talk about in the next chapter are things called random variables. So a random variable is a numerical characteristic that, I missed a word here, that's assigned to each outcome of some random circumstance. So it's called a random variable. So for example, suppose you have a group of people and you want to know how many in that group have type O blood. So if you have 10 people, you could have one person, you could have no type O blood, you could have one person type O blood, 2 people, 3 people, 4 people, 5, 6, 7, 8, 9, 10. And each of those would have different probability because I think type O blood is pretty uncommon, right? Are they the universal donors? Those of you that know about medicine?
I'm O positive.
You O positive? Yeah. So, but the thing is that you could say, I have a sample of X people, what's the chances somebody in that sample is going to have type O blood? And so the random variable is how many people will have type O blood in your sample of a given size. And this next thing, a family of random variables. This lists all random variables for which the same formula is used to find probabilities. So if I have X, which is, say, number of people of, say, 5 with type O blood. So out of that group of 5, how many people can have type O blood? None, right? What else? 1, 3, 4, and 5. And these would all have different probabilities that would be based on how common type O blood is. Does that make sense?
But those 6 numbers are the family of random variables?
And they would have different probabilities for each of them that would change based on how likely or unlikely it is to have whatever thing we're talking about, which in this case is type O blood. And the point is, this encompasses all the possibilities, like because you've got a group of 5, either no one does, 1, 2, 3, 4, or all 5 people do, right? Okay, but the family is all the different possibilities, whereas the random variable is just like one of those. That's all. And 2 different kinds of random variables. So, and we kind of already discussed these. The first one is called a discrete random variable. And this must take a value from a countable list of distinct values. So, for example, this could be the number of dogs in a random house. The point is you have whole dogs, not half dogs, like a Yorkie counts as a whole dog still. A Mastiff is, not 5 dogs, it's 1, right? So if you're talking about numbers of dogs in the house, you could have 0. What else?
1,
2, 3, etc., right? Who knows what the highest point is because some of those mushers have lots of dogs, right?
Generally not in their house, though, hopefully.
Well, we'll say in their possession, okay? So, but the point is that you fall into like a category, right? Whereas a variable that can take any value in an interval, do you remember what that was called? We already had this. Discrete is when you're in specific buckets. Anything in an interval meant continuous, great. So what was an example of a continuous variable?
Length of your arm.
Length of your arm, sure. How about height, right?
Yeah.
Weight. So those are all examples. The star means nothing. I just want to make a symbol. And often those things do get discretized, meaning like you kind of treat them like they're discrete, like you say, oh, I weigh 145 pounds, not 144.37286. Does that make sense? So, but in general, anything is possible within an interval.
So it's a continuous random variable?
It's a continuous random variable versus a discrete random variable, and they're just those two kinds. And you can make continuous into discrete by making boxes or like little bins. Does that idea make sense? You can say, okay, you're 5'1" if you're in between these heights. You're 5'2" if you're in between these heights. You're basically using rounding. That's how you can make those bins. Or think about how age groups in like a race, you take this thing that's continuous, that's age, and you make it into discrete groups. You don't say, oh, you're 6 months older, so therefore you get an advantage or a disadvantage or something crazy like that. Okay, so tell me whether these variables are continuous or discrete. So the number of left-handed individuals in a sample of 100 people.
Discrete.
That's going to be discrete. I'm not sure how we're going to count people who are ambidextrous, but we'll just ignore that for now. But you could make that 3. You could make it like left, right, ambidextrous, right? You could make 3 categories. Time taken to complete an exam. Continuous. Anywhere between 0 and 60 minutes, right? Vehicle speeds at a highway location. Also continuous. And there the interval of possible values is like, 0 up to maximum speed of fastest car ever. All right, number of accidents reported last year at a highway location. That'd be discrete. Can't have half of an accident, right? Okay. So for discrete random variables, we can find probabilities for exact outcomes. So for example, if we flip a coin 3 times, we can find the probability that exactly 2 out of the next 3 will be heads. So like in that case, the random variable is how many out of the next 3 flips are heads, and it could be 0, 1, 2, or 3, right? And the kind of funny things about continuous random variables is that it's impossible to be exactly equal to a value. And this has to do with an area under a curve, but being exactly 5'7" is technically impossible. So for continuous random variables, we cannot find probabilities for exact outcomes, and we're limited to finding probabilities for a range or intervals of values. And the example for that is we couldn't find the probability that a newborn's weight is exactly 7 pounds because weight's continuous, but we could find the chances that they're between some numbers around but close to 7, like 6.9 and 7.1. And if you wanted to get even closer to 7, what could you do to this interval? Make it even smaller, right? Make it even narrower. Does that make sense? Like make that into 6.99 and 7.01, for example. And that has to do with areas under curves, and we'll talk about that more in section 7, 8.5, and 8.6. For now, we're going to focus on discrete stuff. Okay, now just some notation. So we use the following notation for discrete random variables. Capital X is the random variable itself. K is a specific number. The random variable takes on. So for the example about the blood, I was talking about, we had a sample of 5 people, and the numbers that the variable can take on would have been 0, 1, 2, 3, 4, or 5. So it's like your list of numbers that you can actually have occur. And what do you think Px equals K means? What do you think that P means?
The probability of the random variable is a specific number.
Exactly, that's it. The probability of the random variable. Probability. Random variable is that specific value. suppose we find that the probability that 2 out of the 3 children born will be girls and the next 3 births is 3/8. In this case, what is the random variable and what is the value of k? So this one's a little bit confusing, but I think we can figure it out. So 2 of the 3 children born will be girls. Next 3 births. So in this case, we're caring about how many girls there are in the 3 births, right? So our random variable x is the number of girls born in the next 3 births. So if you're at a hospital keeping track of the genders of babies being born, what are the possibilities for x? What things could x equal?
1, 2, or 3.
Almost 0, 1, 2, or 3. Because there could be no girls born. You could have all boys, right? Okay, so that's the possible values for x. Which specific x are we talking about in the statement of this problem?
Oh, 2.
2. We're talking about k equals 2. Does that make sense? A random variable is how many girls, and we were told that the probability that there are 2 out of 3 are girls, so we know k is 2. So what this is saying in this sentence is p capital X equals 2 is equal to what number? 3/8. Okay. So that's not very, very hard. Just trying to dissect it into what they mean. That also isn't the only way to define it correctly. You could have also even said, well, that means there's 1 boy, right? And so then it could be, if you defined the x as number of boys born in the next 3 births, you could say then it's k equals 1, right? So, but don't do that because it's going to make the grader super confused. Try to keep with the terminology as given. Like I could, anyway, yeah, it's hard. Now, this thing called the probability distribution function for a discrete random variable, this is a table that assigns probabilities to all possible values of x. Technically, discrete random variables can be actually like infinite lists of things, but most of the time that you guys are going to see stuff that's like finite. There's only like 3 or 4 or 5 possibilities. Like there's a finite list. Like in this example. So we have a random college, and our random variable x is going to be the number of courses a random student is taking. So x, so we'll have p x equals k, and the specific k is the number of courses. So you know 35% are taking 4, 45% are taking 5, and 20% are taking 6. So at this college, does anybody take less than 4 classes? No. So across the top column of this table, you'll put the possibilities for the x. So, and those are listed as k's because k is a specific value x can take on. So what are the values that can go in for k? 4? 4, 5, and 6. And are they equally likely? No. So what proportion of people take 4 classes?
35.
As a probability, that's going to be 0.35. Does that make sense? What proportion are taking 5 classes? That's going to be
0.45.
0.45.
And 0.2.
And then 0.2. And as long as you've listed all the possibilities, like this top row is all the possible values for x, what should these numbers add up to? 1, and do they?
Yes.
That makes 0.8 plus that 0.2 makes 1.0, right? If we were talking about UAF, we'd have to probably add on 0, 1, and 2, and 3 courses. There's a lot of part-time students here, right? But this college, you just take 4, 5, or 6 classes. It's hypothetical, right? Okay. Yeah, so note that those things sum to 1. Oops, wrong button. So knowing that, so assuming that these values of k are all the values that x can take on, what has to be this last number?
3, 6.
3, 6, yeah, you have to have 1, 6 plus 1, 6 plus 1, 6, and my goodness, can I call it x, please? Plus x has to equal 1, right? So that's 3, 6 plus x has to equal 1. So that number has to be 3, 6 or 1/2. You can see why I don't solve equations with question marks in them. That's just so annoying. How about you figure out the next one?
Represented by an equation mark.
Represented by an equation mark. That's hilarious. Question mark. 0.2, 0.3 plus x equals 1. So what's all that? 0.9, right?
Plus x equals 1. X
So-
equals 0.1.
X equals 0.1, exactly. Okay. Does that make sense? Alrighty. So that table that you have, things you were given in the previous example and the thing we wrote in example 3, those are called probability distribution functions. You also sometimes care about something called the cumulative distribution function. So what this tells you is the probability that your random variable x is less than or equal to a specific value, as opposed to equal to it exactly. Does that make sense? That is called cumulative because you take all the probabilities like up to that point. They accumulate as you go on. So that's called the cumulative distribution function. And then the thing called the cumulative probability and this refers to the probability that x is less than or equal to some particular value. So we're going to have an example of something actually in context, so this will make more sense. But the point with cumulative stuff is you're like accumulating probabilities up to a point, like you add them together. Okay, so this table right there, that's what they call the PDF, probability distribution function. So this tells you the chances that a random person you meet's only eaten 1 meal, 2 meals, 3 meals, or 4 meals. Does that idea make sense? Okay, so what we'll do next to make the cumulative distribution function, which is called the CDF. So we have meals, which is still x, probability. We have like x is less than or equal to k now instead of x equals k exactly. So first we have 1. What's the chances somebody ate 1 or less meals? That's still just 0.1, right? We have nobody in our table eating no meals. Now when we're looking at 2, what are the chances somebody ate 2 meals or less? That means they ate 2 meals or they ate 1 meal. So that'd be you adding these two together. 0.42. But this is 2 or less meals. And what does plugging in 3 mean? That means, and then you add all 3 of those, right? So you accumulate the next one.
98.
Mm-hmm. And then when you go to 4, you get to 1. And that will always happen, won't it? Because Because this last value is always that you've accumulated all the possibilities. So that's always going to be 1. And these numbers are always going to go up because you're always adding on some little thing. Does that make sense? Yes. Go ahead.
Sure.
Okay, go ahead. Yeah.
So is there ever a situation where you would say 1 or more, 2 or more?
These things are for some, they just kind of standardize it and they're almost always measured down. Does that make sense? And that actually is true in the next stuff we're going to talk about as well. So how you usually phrase like x is bigger than or equal to whatever, I don't think that has a name, but then you could just say, oh, if x is bigger than or equal to 2, you can just add up the 2, 3, 4 thing. Did you have a question or was it the same thing? Okay. We're good? Okay, part B says, what is the value of p x less than or equal to 2, the probability that a randomly selected person ate 2 or fewer meals?
0.42.
Yep, 0.42. Okay. Okay, so far I've given you the PDFs. Let's actually find one where we have to make one ourselves. So we toss a fair coin 3 times. I want you to list all possible outcomes and write a PDF for x is equal to the number of heads that you have in those 3 tosses. So first of all, if you toss the coin 3 times, what are the possibilities for numbers of heads you could have? 3, or 2, or 0. Does that make sense? And we're going to list them from 0 up to 3, but you know, that's the basic idea. You have no heads, 1 head, 2 heads, 3 heads. You flip 3 coins, 3 is the max you can have, right? Okay. So, flip 3 coins. Oh, we could have had heads, 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 right? How many ways could we have had 2 heads?
Heads, tails.
Heads, tails, heads, yep. Great. And that's all the possibilities for 2 heads. How about 1 heads?
Heads, tails, tails.
Mm-hmm.
And
Tails, tails, heads. There's one more.
Tails, heads, tails.
Tails, heads, tails. And the last one is
tails, tails, tails.
tails, tails, tails.
Right, small.
Yes. So K is equal to number of times you get heads, probability that X equals a K. Okay. How many different outcomes do you have there? 8, okay. So of those, how many have 0 heads? 0 heads. 1. Let's just put like a check mark next to it because we counted or something like that. How many of them have 1 head? 3. This one, and this one, right? So what's the probability that you see 1 head in 3 tosses? 3/8. Okay, how about 2? Also 3/8. And how about 3? 1/8. And then you can check and see that you got them all by checking to see that these probabilities add up to 1, and they do, right? You could do a similar thing with having 4 coins being tossed, right? Just that then you'd have 0, 1, 2, 3, and 4 as your possibilities, right? Okay. This next one's also kind of a fun question. Some people do operate this way. A woman says she's going to have children until she has her girl, or she has 4 children, at which point she's done and she's stopping because 4 boys is enough, okay? Does that make a crazy question? But that's the, okay, so maybe this happens in life.
It does.
So,
It does.
it definitely does. And our random variable x is the number of children she has, because she could have 1 or 2 or 3 or 4, but no more, right? Okay. So first, let's list the simple events. And she's going to have a kid until she has a girl. So if she has 1 kid, it's because she has a girl on go 1, right? If she has 2 kids, what does she have to have? Boy, girl. 3 kids, it's boy, boy, girl. 4 kids, it's
Girl or boy.
or all 4 boys. So those are the different simple events. Girl, boy, girl, boy, boy, girl, 3 boys and a girl, or all 4 boys. Okay, those are the possibilities. Okay, part B, does that make sense? Okay, part B says write the probability for each of the simple events. So, event, and you use the fact here that births are independent from each other.
Okay.
So, girl, what's the chances of her having a girl? 50-50, so 0.5. Does that make sense? For boy, girl, you take probability of boy, which is 0.5, times probability of girl, which is also 0.5, and that'd be 0.25. How about boy, boy, girl? 0.5 cubed, right? Because 0.5 for the boy, 0.5 for the boy, 0.5 for the girl, right? 0.125. And then how about the boy, 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 girl? That's going to be 0.5 to the, which is 0.0625, I believe. In this case, definitely don't round those, okay? And then the last one is boy, 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 and that's 0.0625 again, right? Because that's still 0.5 to the 4th. And do you believe that those add up to 1? Yeah. The 0.0625 plus 0.0625 makes 0.125, and then those 3 last ones add up to a quarter. Does that make sense? Okay. So C says to find the probability distribution function for X. So in this case, X is how many kids she has. So K equals number of kids. Probability that X equals a specific K. So she doesn't have no kids, but if she has 1, what's the probability with which that happens? Just a half. Yep. How about having 2 kids? 0.25. How about having 3 kids? 0.125. And then 4 kids is the one place it's a teensy bit special because she can have 4 kids in 2 different ways, right? She can have 3 boys and a girl, or she can have 4 boys, right? So you add up those 2 probabilities you found in part B, and they add up to 0.125. And there's the PDF for number of kids. Okay. The part D about drawing a picture is not very hard. In example 8, I think I'll just start with that next time because I don't want to